So hello everyone. Today I'm mainly talking about some of the recent papers about open domain question answering. So this topic I have already presented about 1 quarter before about open domain question answering, and I will briefly recap the overall framework and the, the the most standard model so far to deal with this task. And also later on, I will introduce some of the recent papers that try to jump out of this basic framework and do a good job. So the basic framework of open domain question answering is defined about 4 years ago by Chen Danqi in her famous paper DRQA. So that given the question, for example, how many of Warsaw's inhabitants spoke Polish in 1933, the challenge of open domain question answering is that we don't provide you the context. For example, when you do the reading comprehension in middle school or in high school, you probably have a passage that contains the answer of this question. But for open domain question answering, normally we will assume that the relevant passage is not given. So you need to find the reasoning path or supporting documents by yourself. And the most standard framework is that we utilize the Wikipedia as our like the knowledge our knowledge base where we retrieve the relevant passages, so that we rely on a uh, retrieval module to retrieve the corresponding article. For example, the article with the title Warsaw, and the correct passage that should be retrieved is the one that contains the answer. For example, the answer for this question is 833,500. So if this passage contains the word of this answer, then this should be regarded as the ground truth article that we should retrieve. So in the old days, people utilizing the sparse retrieval like method, such as KFIDF and BM25. And this kind of the methods actually worked quite well in until like 2018. People try to learn the like the dense embedding for better retrieval, but it doesn't perform better than single TF-IDF, mostly because that the training samples in the question answering data sets is very limited. So if people want to train a good text similarity like the model to serve the purpose of like doing the retrieval, people should utilizing some of the unlabeled data or the other data resources, but that kind of resources are not 100% suit the QA. So this is like the first challenge. Um, and also, uh, before like 2018, doing the fast similarity search over a super large uh, embedding space is very slow. So suppose that the Wikipedia have about 21 million of the passengers, so which is like very large. When we do the similarity search of the dense embedding, we normally need the dot product between two vectors. And this kind of the computation is very slow. Oh, okay. So this kind of the calculation is very slow, or you before 2018. But recently, since lots of work on how to do the fast similarity search, utilizing like the fast index or like the randomly projection or like the build, um, there are many tricks to do that. And also in 2017, the researchers in Facebook built a tool called Face, which I sent like last week uh, to Zijie. Um, Based on this tool, doing the fast similarity search is very quickly in recent days. So, and also based on the progress in the pre-trained language model, we found that we don't need too much of the supervised data to train a good similarity text similarity model. So both these two, like the breakthrough, uh, make the dense embedding possible. So that we see in the last years in MLP, there's a work called dense passage retrieval conducted by the Facebook AI research. The basic idea is super simple, that they try to decompose the similarity between the question and passage as the dot product of two separate embedding and train with different encoder. So that we all know that if we concat the question and the passage, we will have the interaction like of the token in the question and token of the passage, and makes the similarity more accurate. However, this is not feasible in real because that the whole passage space is too large. We already say that we have 21 like 21 million of the whole passages, so that we cannot afford doing the batch computation of by concatenating each question with all of the passages and calculate similarity one by one. So that a more computation efficiency way is to do decompose them into two separate encoding procedure and to get this text similarity. In this way, there's no interaction between the question and the passage. But for most of the question that don't require too complicated reasoning, such method is already enough. And the most important thing in this PPR paper is how to select the negative samples. And uh, here I show how to prepare the positive and negative samples. For positive, it is very standard. Either it is the ones that provided by the training datasets, or we can just get the passage that with the highest text similarity score and also contain the answer. So these are the positive passage. For the negative, it is tricky. So because if we just randomly pick up a passage over the super large space, then the training will not provide enough training signal to guide the model. So that in this paper, they simply utilizing uh, the high BM25 score but not containing the answer as the hard negative string. So in this way, just utilizing the supervised QA samples in the provided by the datasets, they can already train a good like the passage retrieval model. Okay, so this is like a conclusion of this work. Yeah, so that we don't need very expensive pre-training like the task specific like the QA specific pre-training like utilizing the large amount of the text similarity corpus to train a good retrieval model. But this is okay for the modest-sized QA datasets like natural questions, which contains about 20,000. And also the work I recently do also observe that if we design the pre-training like carefully, then such procedure can also improve the performance. Also, there are also some of the finding that joint training versus pipeline training. The joint means that we train the retriever and the reader jointly. Pipeline means I would only train them separately, which is faster. And like the results show that doing the pipeline can even perform the results, so that joint training didn't help too much. So that the most standard way is just doing the pipeline, which we train the retrieval from one task and train the reader from another task and put them together. Okay. Yeah, so DPR paper is 1 year ago. I remember I have already introduced this in the last quarter, but not in the too much of the details. The idea is very simple, but the breakthrough is that it shows that doing this kind of dense retrieval can work. So on this leaderboard, we can see that at the time of 2020, the DPR is the one that achieved very promising results over the many of the famous open domain QA datasets. And DPR is like the standard model that follow the retrieval reader framework. Okay, and later on I will show some of the papers that try to jump out of this retrieval reader framework and doing something else. For example, the first one is try to replace the reader, the extractive reader, with a generative model. And also we can even think about utilizing the generative model like a GPT to replace the whole retriever and the reader. But this doesn't perform too well. And also finally, there's one paper still by Chinese group that tries to replace tries to remove the reader and only utilizing the retriever to get the answer. Okay. Any questions so far about the DPR? If no, I will go to the first paper. Yeah, this is like the newest paper 1 year before, and the from the title we know that this is like a combination of a DPR retrieval and a generative model. So that will replace the reader with a generative model to directly get the answer. The overall framework is not very complicated. So that given a question, the first step is still utilizing the retrieval model to get some of the context. For example, if the question is, let me see. For example, still the previous question, how many of the world's inhabitants spoke Polish in 1933? And the first step is still to retrieve some of the relevant text. And based on this text, they utilizing the generative model to get the answer. And they have two variants of this generative model or generative objective. The first is given a question, they just retrieve a they just based on the question to retrieve the documents, and based on the document to autoregressive they generate the text. And since they can obviously there could be multiple documents that are relevant, so in their setting they just retrieve the top k relevant documents. The other objective called the token level objective is that suppose at each stage they already generate about I tokens of the answer. So the next step they can based on both the question and the answer to and the already generated answer to retrieve the relevant text, and based on them to generate the next hop of the answer, next token of the answer. So in this way, based on different contexts of the generated answer, the retrieval can get different results. Yeah, the the idea is very like straightforward, just to combine the generative model with the retrieval. But the final result is somehow interesting. So they utilizing DPR I have already introduced as a retrieval model. I use a BART, which is a generative model proposed by Facebook as the sequence-to-sequence generative model. And since these two models are both differentiable, so they can join train these two components auto sequence to like end to end based on the question and the answer. And in this case, they don't require any of the intermediate like the supporting facts. For example, for the question, which one should be the, the corresponding documents that that is the ground truth of the retrieval model. In their cases, they don't require the ground truth or the golden label of the intermediate text. Also, another benefit is that since the generative model can generalize well, so that they don't really require the answer being exist in the retrieved intermediate text, so that like both the out of domain generalization can be improved, and also as I said, they don't require the ground truth labeling for the intermediate text, and that kind of labeling can somehow be incorrect, because as I previously showed, in DPR they utilize for those documents that don't provide the ground truth, they use like the high BM25 score that contain the answer string to be the answer. But that is not always the case to be the ground truth. For example, suppose I ask what is the birthday of some person. The kind of the birthday, for example, 1996, can occur in many of the documents. Even though we retrieve the one with high BM25 score, that doesn't mean that that document is true. So utilizing the generative model, they can alleviate such labeling issue. So finally, I can show you some of the accuracy results. So for some of the data sets, for example, for natural questions, replacing the extractive model with the generative model can enhance the performance over the DPR. Their model called RAG, the Retrieval Augmented Generative Model. For some, they didn't perform quite well, but at least for open domain QA, it performs very well compared with the previous, like the CFR. And these two are the data sets with like factor tracking and some of like the long question, long text answer, which means that the answer is not just a single phrase, but could be a one sentence. For those of the like the data sets, their model, um, in those of the data sets, they only have to compare with the generative model, and compare with the base generative model BART they use as one component. Adding the retrieval module can significantly, not significantly, at least for Jeopardy, they can enhance the performance about 2 to 3%. Okay.
So Ziniu, I have a question in terms of the evaluation. So
Yeah.
if the result is directly coming from the extraction, then I think it's easier because you just compare whether like those two strings have overlap or something. But then if we allow the model to generate the answer, actually even the answer does not really contain any string in the ground truth, but it could still be correct. I just wonder, in the evaluation, do they have some spatial treatment for this issue?
Yeah, I understand your concern. It's like there could be some paraphrasing in the answer they generate, but at least for the table one, they still utilizing the exact match to evaluate their model, so that in this way it means that their generated answer could be correct, but they still be treated as wrong in their cases. So the number could be even higher compared with the reported answer, reported score. But this kind of situation also like occur in the extractive model. So in some cases, our extractive model can be relevant or correct, but they are not the correct answer. So that we just treat it as not as incorrect based on the exact match criteria. Yeah.
I see. Then is there any kind of more advanced evaluation? For example, ask for example, the mechanical Turk to label the uh, the results and try to compare two systems.
Yeah, so in this paper, there's a data set called Jeopardy. This QA data set is like generate somehow like the long-term answer. And for this kind of the data sets, they provide the human evaluation. Let me check their accuracy. Uh, can you see the like this web page?
Yeah, I see a paper.
Yeah, there's a paper, and this table 4 is a human assessment for the Jeopardy question generation task. Yeah, and for their evaluation, they simply do like the AB like a comparison. They compare their model with the BART model, so that just like compare whether which one is better. Yeah, so that it obviously could do some of the like a Turing test or the other kind of the task to assess the generated answers quality. Yeah.
Okay, I do not quite understand the factuality and the specificity here.
Oh, these are two type of the questions of Jeopardy.
Oh, I see.
Yeah, so one is like something like more factual questions. The other is more like I don't fully understand the term, but it's more like a more general questions.
Mm-hmm.
Yeah. Um. So here are the some of the visualization of this model. For example, previously I have talked about introduced the RAG token model, which that given the current generated text token, they can retrieve the corresponding like the passage. So which means that at a different position, they can retrieve different text. They use this example to show this result. For example, if the generated answer, the question is like the sun also rise is a novel by this author of a farewell to arms, and at the position of the sun also rises, the ground truth their predicted retrieved model retrieved text is document 2, which contains the information of the sun also rises. And if they are at the position of a farewell to arms, they can retrieve the corresponding text, which means that their like framework utilizing RAG token is very flexible and can somehow like generate more complex can handle more complex questions that contain multiple entities because they can based on different entities to retrieve the different like the passages. And here are the generated answer. So as you can see, MRS Marco is like the long, like the um, longer answer, which contains more than a single phrases. It could be the short sentences, and utilizing their framework, it performs better than the single BART, which doesn't have the retrieval module. And results show that it seems that their result is more promising than the single BART. Okay. So here is the RAG paper, and it's still a paper 1 years before, and the lessons we can learn from this paper is that maybe we don't need the explicit retriever. And oh, no. So the lesson we learn from this paper is that we can somehow replace the reader module with something else, for example, generating module, because recently the BART is still also trained on the wiki, but recently we have seen more like the powerful generating model like T5 and GPT-3, so that probably we can utilize a more advanced generating model to do some of the complex reasoning tasks for the question answering. And also, concurrent to this work, there are many other works tries to directly generate the answer. Yeah, but actually the accuracy in this line of research is not very well. And this kind of research called no explicit retriever. So that the quick question is like, can we use the pre-trained language model itself to act as knowledge storage? And instead of explicitly storing all the tags and searching among their dense and sparse representation, can we directly utilize the language model to obtain the answer? So that people treated this as a language model as knowledge base. For at the stage of GPT-2, actually the performance is super low. Utilizing the GPT-2 without any fine tuning, which is like a zero shot to sagging, they can only achieve about 4% of the accuracy on natural question data sets. So yeah, which is not actually do quite well. But at the GPT-3 stage, with much more like the training passages, and they added some of the future experiments, the result is a little bit higher. So that GPT-2 is 4%, and GPT-3 with zero shot can have like 14%, and with the few shot setting, which means that they can add a few like the tuning samples to fine tune the models, they can achieve about 30%. As a comparison, DPR is about 40% and RAG is about 44%. So 30% of the EM accuracy is not very promising accuracy, but it still shows that even without the retrieval, utilizing the generative model itself can handle some part of the questions. And the Google tries to propose a T5, which they call it fine-tuning leads to improve the performance. So during the training, instead of just a single generating model task, they also add many of the supervised data sets, such as machine translation, summarization, and question answering. And they put all of their data, this kind of supervised data sets as a fine-tuning task on the right-hand side of the T5. So in this case, during the pre-training stage, it is somehow similar to the meta-learning procedure. So that in the one epoch, they train based on the unsupervised data sets, and then they can fine tune on the this supervised task to somehow pick up the most the generalizable model, and they somehow pass the gradient to the original the unsupervised learning, so that the final pre-trained model can be well adapted to any of the supervised tasks with a few fine-tuning steps. And with this model and fine-tuning on the corresponding data sets, they can achieve better results than like GPT-3. For example, in natural questions, we previously said that GPT-3 only retrieve about 30%. K5 actually they can retrieve about 34 or to 36%. And this SSM is another like the pre-trained task that designed specifically for QA, proposed in real QA retrieval. This is proposed in real model. Yeah, but it still didn't outperform the DPR, which is like the retrieval and generative framework. Okay, I think here is all about the models of generative only models. Do you have any questions? Yeah, the current conclusion is that if we didn't like rely on extra knowledge, like the retrieval based on the Wikipedia, just based on the generative model itself, it cannot get much better results. Uh, yeah, but for some of the data sets, for example, TQA, is surprisingly get better results. Probably it's because that those data sets are much smaller, and with this smaller scale, maybe the retrieval cannot get uh, like the sufficiently better uh, performance than a pure generative model. Okay, a summary: the large amount of language model pre-trained on unstructured text can attain competitive results in OpenQA without accessing external knowledge for those smaller data sets. But the performance is largely impacted by the model size. The T5 model is actually like 11 billion, so, which is like a T5 big, which is much larger than the single BERT and the Roberta, and it can match the performance with PPR with 3 BERT-based model, so which is uh, only about 330 million parameters. Yeah. So so here are the two papers that tries to utilizing generative model to serve the purpose of QA. And next, I will present a very interesting paper still by Chendanchi's group that tries to remove the reasoner module, so that they claim that utilizing the retrieval itself can answer the question if in the granularity of phrase, which means that previous retrieval is conducted in document level, so that for each question, they just they utilizing the question to retrieve most promising document, and from it to have another step to extract the answer. This paper tries to like do it in the more finer granularity, that based on the question that directly retrieve the phrases from the super large Wikipedia. Yeah, this is like their high level idea. And if we write it in the mathematical formula, it's like this S could be regarded as the final span as the answer. D is the document corpus, and the Q is the question. The retrieval reader module can be decomposed into two steps. First is retrieval based on question and document, document corpus to retrieve the most relevant passage documents like DJ1 to DJK, and from each of the documents, they try to extract the most promising, like the span. This is like a retrieval reader framework. And this phrase retrieval model tries to directly get the final answer occurred in the passage as the one they want to retrieve. So that you can see from this figure, given the question, they get the start projection and the end projection. And based on these two projections, they directly retrieve the start token and the end token. In this way, the final span is directly the answer. So although the idea seems very straightforward, but they are
I have
so
a question. I have
oh
a
yeah,
question. So here, retriever reader is what existed before,
yeah.
and
Yeah,
that phrase retrieval is what they suggested.
yeah.
I see. And then why do they somehow, so exactly, could you elaborate more about the phrase retriever? Retriever reader, I think I got it. Actually, let me trace back. For retriever reader, how is the K prime determined? Is it based on the threshold value of some kind of similarity, or the K prime is given as a hyperparameter?
It's a hyperparameter. In most cases, it's just the one.
I see. In most cases, it's just one. Okay. So it's a hyperparameter that we have to provide, and then from there we find. Okay, so that is retriever reader. And how is the phrase retriever? Could you? What is S? What is S? S is what?
As uh, for the answer we want to get, most likely we will get a span, which is like a start token and the end token. It's called span, SPAN. So S is like referred to span. So the phrase retrieval, you can regard it as that we treat all of the word or token within the Wikipedia as the one we want to predict. So that what we want to predict is whether one word within the whole Wikipedia space is the start and whether one is the end. So that compare with for example, the do it in the document level, we have 21 million documents. Currently, we will have 60 billion phrases in the whole Wikipedia. So for example, still take this as an example. This
Hold on. May I ask a question?
Yeah,
so let's say there are two documents, and
yeah,
then so out of how many pages that Wikipedia may have, let's say there are two documents that contains Barack Obama exactly in that sequence.
Yeah.
In that case, do they get considered to be the same start and end because they share the same words, or they are different start and end?
They will be treated differently.
Differently, okay.
Yeah, so even though a single phrases will occur multiple times in the passage, since their context is different, so maybe only one of them is match our question. For example, if we want to say that who is the president of the United States at 2014, then maybe the Obama phrases at the context of United States president is the one we want to retrieve.
Okay, so at least now I understand what S is. So can you explain more about what E sub S and E sub Q are?
E sub Q, which is E sub
so when I look at the phrase retrieval formula, the transpose of E sub S is multiplied together with the E sub Q. What is E sub S and what is E sub Q?
Yeah, ES and EQ is two like encoder. So similar to the dense passage retrieval, they're utilizing different separate encoder to encode the question and the phrase. So here they are encoding in the like the granularity of phrase instead of passage. So after that, they will have question embedding and the phrase embedding, and then they can do the like dot product to determine which token is the start and which token is the end. You can
and how here E sub S, so E sub Q I think is reasonably clear. We just have to pass the query to the whatever encoder and we get it. What is S comma D? I'm not sure exactly what is S comma D, like the first part in this multiplication.
So if you're familiar with like the BERT or the so-called contextualized word embedding, currently if we want to get embedding of a phrase, we are not just based on the phrase itself. We will treat them in the context of their surrounding text. So that go back to your previous example, even if we have Obama, their embedding will be different based on their context. For example, the Obama in the context of president will be more close to the like the role of president. So that what we will do is that we pass for example, a passage to a bird, then we will have the token embedding of each word within a context word embedding of each word within the passage, and each of them is the what we will utilize as to predict whether it is start or end. For the question one, what we will get is a sentence encoder. Normally, we will just utilizing the first the BOS token as the output to get a sentence embedding. So this one is a sentence embedding, and this one is a word embedding.
And how did they intuitively justify that phrase somehow this formulation is better than retrieval reader? Because I don't really see too much of a benefit of doing it this way.
Oh, so the most straightforward advantage is in the computation efficiency. So here I can directly jump to the like the final table. If you are doing the retrieval and reader, you need to firstly retrieve the document and then parse the document and then get the answer. And in this way, since it's the pipeline, doing it will be much slower than to do it in the phrase level. So as you can see, this is a number of questions per second. Utilizing the GPU, their model can parse about 20 questions utilizing a single GPU per second. And the original or previous like a retrieval reader model can only handle one question per second. So this is like the efficiency perspective. So for the like the final accuracy perspective, their result and also intuitively they didn't get better results. So so this
Why
is like
this is faster
yeah, this is faster.
But in the retriever reader framework, we can actually first select the most promising passages, right? And then we try to select the most promising span.
Yeah.
And here, there are much, much more span than the documents. So, but there's no pre-filtering. So why in the end, it's going to be even faster?
Because as I said, doing the like doing like the where can I find it? Doing the fast doing a similarity search over like the like the ON N documents right now is much like small faster than ON. So currently, based on some pre-index, they can do it in the like the more similar to constant time. In this case, even if the search space currently is much bigger, so currently they will have 60 billion search space compared with 22 or 21 million search space, because of the token is much larger than the is much more than the documents. But
is it because of phrase? Although there are more phrases, but the size of each phrase is much smaller, and then they use like maybe hash index, so then they can quickly locate which phrase is most similar to the query.
No, this is not the case. In the indexing, they only store the d-dimensional embedding. So for this, for the indexing and the similarity search, these two their behavior is similar, and obviously doing the retrieval is faster than the phrase. The bottleneck is after you retrieve the documents, you still need to like process it and pass it to another model, the reader model, to get the answer. And this kind of steps will take much time.
I see. So can I understand this way? So somehow the current model, they combine the retriever and reader into the same thing. So they don't have to ad hocly compute whether a phrase is similar to a query because it's already kind of pre-processed.
Yeah, you can think about it as that. So they don't need like the pre-filtering step of the retrieval to like narrow down the search space. Yeah.
Why does the reader take so much time? Because you already filter it, so you only deal with a small, hopefully small number.
Yeah, probably I can say that as this. So the reader needs to concat the question and the context into the batch so that they cannot parallelize in like a million level. For if you want to fit it into a GPU, normally you can only fit about 100 like the as a batch because of the GPU memory. But for like the since in their framework they have a separate encoder of the passage and the phrase, so that they can do both of them separately and they don't have an intermediate step.
So somehow I'm not getting something, I think. So the way that I understand about the past work about retrieval reader model, they call it retrieval because they use a search engine to actually identify top 5 or top 10 pages that seems to be relevant to the query. And that is immediate. We don't have to do anything. We can use traditional search engine to identify top 10 candidates. And then only for those 10 pages, we pass them through whatever the matcher or reader to identify the span that best answers that question. That is traditionally what have been proposed or what have been actually implemented. And somehow I think in their work they somehow twist that a little bit to somehow to imply that that is not how things are done, or am I somehow not getting something? I'm really a little bit not sure.
Yeah, I think what you summarize for the retrieval reader is very correct. So traditionally, this retrieval is like a search engine. The only difference is currently we can replace a sparse search engine as an embedding-based search engine. For the phrase retrieval, it's like they directly retrieve the most relevant like a phrase in the document as the so they are also a search engine, but the granularity of the search engine is in the phrase, not a document. So given the question, they will directly retrieve the single phrase like Barack Obama as the most relevant thing to your question. And this relevant could be as close to directly answer this question.
I'm still not getting something, but I think we can continue. I think those are more of a side point. Maybe
Yeah,
now
so
we can.
I'm also not getting why it's fast. So I'm still not quite getting it. But anyway, you can move forward.
Yeah, I think we can continue.
Yeah.
So are you not very sure about the motivation part or the implementation part?
Well, if the motivation is to speed it up, right? Then I'm just not getting how this. Maybe I'm sure I missed something, like how the speed up is accomplished compared to the retrieval reader model. If the motivation is to get it more accurate, maybe I can guess probably more accurate, but
I agree with Wei. I think that is
Yeah.
exactly my impression. But I think we are missing something. So I think we can
No,
continue.
I
Maybe
just
as
feel
we
like
listen.
I'm missing something. What's the, because if you tell me how they does it and ask me what they accomplish, like I'm not sure what they accomplish, right? What they're able to do better than the traditional model.
Yeah. Yeah. In terms of the speed up, what I can think about is that after you retrieve a document, you still need some of the pre-processing step of that document. For example, tokenize this and append it to the question and feed it into another model and that model is much complicated than the retrieval one, because most the retrieval as I show is like a 2-tower model, get a separate embedding and doing the dot product. But for like the reader model, it normally takes I can think about tell like this. A question is normally just about maybe 100 token, but the retrieved document could be in like a 4,000 tokens. So that apply that to a bird will take a much longer time than like doing the ES step, doing the EQ step. This ES step is doing it is already pre-processed. so that after train it, we will firstly build an index of the whole, either the document or the phrases. So that although this take a lot of time, but this is pre-conducted, so that it will not affect the runtime situation. The only runtime is EQ, but normally the question is very short, so that doing the EQ is very fast. But if we get the document and append it to the question and throw it to a reader, then the BERT will take the input a very long text, and that processing will take a long time.
So
Okay.
for the reader part, why can't they do something, also do some pre-processing? They don't have to,
Yeah.
do that on the fly, like append them and put it, give it to BERT, right?
Yeah. So currently, this is like the retrieval model. As I said, the question and passage will be handled by different BERT model, and this kind of model will lack the interaction between each other. For the reader model, what they will do, or most of them will do, is concatenate the queue with the passage, so that a token in the question will interact with the passage of the token in the passage. In this way, based on different question, they will have different output. If you just do like the pre-processing of the passage, for example, all the word embedding is pre-computed of the passage, then it most likely that based on different question, the final answer will be the same, which is not very ideal. To this extent, they have to do it in a runtime instead of pre-computed.
Yeah, so to my understanding, it's like for the old model, after we retrieve the document, and the computation is still based on the query. So the extraction operation actually is quite expensive because we really need to know the query, and not too much things can be done beforehand. But right now, they somehow just do some sort of pre-processing. They turn all those documents into this phrase level. So of course they increase the phrase a lot, right? We are going to have this pre-processed 60 billion phrases, but then they can just learn an encoder for those phrases. So, and I guess they rely on the index heavily because there's 60 billion. Once the query comes in, they can use like constant time to retrieve the most promising phrases. Very similar to our G-hashing idea. Just leverage the graph query and a binary code to retrieve the most promising ones in the database.
But for this type of retrieval, right? So I mean, it's the phrase based, and then once, because when you build this 6 billion phrase index, right, you still do not consider the query, right? Because the query hasn't come yet.
Right.
And then when you have the query, you do the encoding of the query, kind of the whatever you just said about the limitation of the reader retrieval, the retriever reader part, the reader part still applies here, right? Because you still don't.
This is probably why the final performance is a little bit lower. Even if this paper adopt a lot of tricks to enhance the performance, but the final performance is still lower than the DPR paper, because the most important thing is that they lack the interaction, so that their phrase are query independent.
Right.
Okay, I think I got it. I have one more question. So if you actually do it, pre-process it to compute that, essentially that embedding of the S for over the entire document corpus, how is the boundary of the phrases determined?
Oh, they didn't determine the boundary. It is determined in a runtime. So for example, there could be a sentence like Barack Obama lived in like a White House. This phrase, this could be the answer for one question, and the Obama could be an answer for another question. This kind of the start and end will be computed in the runtime.
In the runtime.
Yeah. So
and then once you somehow so then how do you compute the embedding when you pre-process it? We compute the embedding for each word, context-sensitive embedding for each word, or how do you do it?
Each word, or actually it's each token. The token means that each token means that a longer word could be separated into multiple tokens, and so that they will compute it in each token. Yeah.
And then how do they combine if there are for every possible sentence or what did you call it? The span boundary for that sequence of embeddings, how do they somehow combine them into the same dimension?
What do you mean?
So if I have, let's say, three token span that I may have to potentially consider as a match. Now, if individual token has, let's say, 100 dimension, now we have 300 dimension embedding.
So they will calculate the start and the end separately. So they will not do in the span level. They are doing in start and end token level. So they will calculate each token to be either a start or an end. So that they only need to predict the start position and the end position, and the start and end position will define a span.
I see. And then they compute the similarity between start of the span and start of the question and end of the span and end of the question.
This start of the question is not actually the start of the question. It is just another encoder. So that it's just a start projection of the question and the end projection of the question. Yeah.
Okay. Thank you.
And then this start and end thing are done like jointly, right?
Yeah. So I believe they will have some of the like the hard-coded criterion for the hard start and end. For example, they cannot be in different documents, and they have some like longest like a threshold of the words. I didn't see that in their approach part, but I believe that should be.
Well, they must have, because otherwise they could have like you have a three mentioning of like Barack Obama, right, somewhere, and then you may decide I mean, the first occurrence of a Barack may be a good start, right? But then the second occurrence of Obama may be a good end, right? But then that doesn't make sense, right?
Yeah. This is like the general question about even the reader. The original reader is
right. They must have something, to have a constraint or something, even solve the constraint there.
Yeah. What I implemented is just within the longest token size of 10, we predict the span which have the highest score. I don't know how they implement it because they currently didn't publicize the code, but I believe they will have some trick there. Okay, so let me go over the implementation tricks. So this part maybe is not like a very in principle, but it determines the final accuracy quite a lot. So in summary, they will have three language models.
Can you go over what these 3 or 4 diagrams mean exactly? How they, like, at what stage these are somehow processed?
Yeah.
How the outcome of each of these will be used for the final computation.
Yeah, this is what I will try to go over in the next few slides.
Okay.
So firstly, I will introduce the first part. So how to do it in the like the common way. So they will have 3 language models, which means 3 birds. So for the question, they will have 2 birds to encode them to the question start projection of the question and projection of the question, which determines as this. This EQ actually are 2 birds. So they will utilize 2 separate birds to encode them into 2 like embedding. And for the phrase, they will have a single bird with 2 output like a linear to get the H start and H end. Yeah. So this is like the first diagram. And after doing so, in the runtime, if they want to predict which is the highest start token, they just utilize the start projection of the question, do the similarity search, cosine similarity search to the phrase, to the token, and the end to the end. Yeah. So they do it in both the training and do it in the training. And after they train it, they can fix the phrase encoder and build the index of
Hold on. So the A is initial training.
Yeah, the first step of the training. Yeah.
First step of the training. And then we have 3 bolt encoders that are being used right now. One is phrase, what is taking P as an input, which is the original like corpus. And the other one is Q, but Q has 2 birds that we are using. One of them is for the start and the other one is for the end.
Yeah, yeah.
And then we start with the BERT initialization, whatever pre-trained BERT model. And then here what we train is the fine-tuning.
You mean the diagram A?
In diagram A, exactly what do we train?
To maximize the things we are for each question we know the answer, so that we can for each answer we can know that which token start is the ground is correct, so that we just maximize the each of the token that is the answer.
I have two questions. One is when you say train, it means fine-tuning the BERT embedding, right?
Yeah.
And then second, this one has one positive and billions of false positives or billions of negative. How do they train it exactly?
Yeah, I will introduce them later. So the negative sample.
Okay, so you'll talk about that later. Okay, good. Okay, so that I will hear later. Okay, good. Okay, please go ahead.
What is K here?
Just a document. Document
Okay,
K.
document.
So for each, for because this token is like inside this document, they actually don't need to consider two separate documents to be concatenated to each other, because they are not actually interact, so that they will process each document separately to get their phrase token.
So how we can have multiple phrases in the same document?
What do you mean multiple phrases? They will get multiple token, which is a word. So this step is simply get the word embedding of a document, but they have two versions of the word embedding, which is the start and the end.
So do you mean every word or every token in the document will have start and end?
Yeah.
But then it could be like many start and end pairs, right?
Yes, and as I said, they will calculate the start position and end position into separately. Although it is jointly, but they just calculate these two in parallel. So they are not first fix a span and then predict whether this span is good, but instead they will predict whether a start position is true and whether the end position is true.
So do you mean that actually because they're going to kind of freeze all those phrases, so all those phrases will be determined by the current training data set, that they will not grow into some new phrases? Otherwise, how they can do the index for that?
So the index is also at word level.
Okay.
So whatever index is still 60 million about like the word, and then given the question, they will predict whether one of them is start and one of them is end.
I
and
see.
Based on the start and end, they will define the span.
Okay.
Yeah. So after we trained this model, we fix the phrase encoder, and
So they have two index? One for the start, one for the end, or?
Yeah. They will have two index.
Okay.
Yeah, and after that they can fix the phrase encoder to index it, and then they wait a minute. Yeah. So to answer what is a C, maybe I will introduce later, because there's a few steps I'm missing here. So firstly, let me talk about answer John's question about how to select the negative sample in the step A. So as we say, the negative sample is very important when we do this kind of the contrastive learning. In the document level, we want to extract the most similar ones but not contain the final answer as hard and negative. But in the step A, since for for each of the phrases, they don't have too much of the complexity to get to those harder samples. So what they do is like the single passage training. So like for each of the document, for some of them they contain the correct answer. So they only for each question they only utilize them as the training samples, and they will maximize the ones that is true against all the others. So that this is in the single passage training. They don't utilize the tokens in other documents as the training samples here in the first step. Did I clarify it?
Oh, I think I got the basics, but I still need a little more detail to really understand it. So let's say I'm given a document, right? So this is the only document that I'm looking at right now. And
Yeah.
from there, within the document, because I have training data set, the questions and the matching span, I know what is the correct span. That I know. Now, for negative samples, how much is there a fixed number of negative samples that I generate, or how do I determine how many negative samples I will choose from that particular passage?
In there, like the settings, all the words within the documents are negative samples.
Say that again. So, what?
All the other words in this document are negative samples. They don't have the so in implementation, since we will like a set a largest number of the word of a passage. So each passage have a fixed number of the token. For example, 2000. And among these 2000, we know that one of them is start and one of them is the end. Or maybe multiple of them are start and multiple of them as the end, depend on whether like an answer appear multiple times. And the negative samples are all the other words that are not the start and the end. Did I?
How there are, let's say if the passage has 1,000 words.
Yeah.
Then roughly about 500,000 passages there are.
What do you mean 500,000?
I'm sorry, passages, 500,000 spans there are. Because out of 1,000, each of them can be a start. And then once you determine it, the other half, we can actually.
Yeah, this part I have said previously, they will predict the start and end separately instead of first determine the span and predict it.
What does separately mean?
So you can regard it, we have two tasks. The first task is to predict which word is the start word. The other task is which word is the end word.
Yes, and?
So that you don't need to firstly determine which span we want and predict whether this is the correct span. What we will really do is to predict which one is the start word and which word is the end word, so that we only need to consider 1,000 word as the like the search space instead of like a combination.
I see. So what they do is they try to, so they first train it based on the start. So for every word or every token in our passage, we have given the current embedding, we compute their similarity against whatever question that we have right now. And then we have a single positive and 1,000 false, 1,000 negative. So you train it based on that. And we train again based on the end. That's what we do.
Mostly is correct. The only difference is that we are not doing it in two steps. We will calculate these two laws and add this laws together and calculate the back propagation.
I see.
But
We just
all the other are the same.
Yeah. Okay. I think I got it.
Yeah, but this procedure obviously have many limitations because you only consider the phrases within your document, and mostly many of the like the other tokens are not that hard enough. For example, if we are saying that who is the president in 2014, maybe Obama is the one, but there are multiple other hard choices like Reagan and Clinton, and those are not necessary to be appeared in your like passage. So they will add another third stage, which they call the query side fine tuning. But actually, what it will actually do is that after they get fix the phrase encoder, and then based on the question, they will retrieve. They will select the top K, like the predicted start and end, or you can call it a top K span. And among these top K spans, maybe only part of them are correct, and all the other are not correct. For example, when we are saying still the president's case, the Clinton will be retrieved, but that might not be the answer for you for this specific question. So at this at this stage, they will utilizing all the other retrieved the span of their previous model as the negative samples. They are not the answer as the negative samples. So as you can see, the as Q is all the spans they retrieved based on their model, and they will like maximize the ones that are match the ground truth answer. So adding this kind of step, like their contraction can be done in the more like harder way, so that there could be some of the harder negative samples. Yeah, I agree that this is very complicated, and probably they can think about how to improve it by combine the first and the third together. Yeah.
Do they assume for each query there only one answer?
This depends on the data sets they have. For the natural questions, sometimes most of the questions we only have one answer, but there are some answers that this data set provides some paraphrase. For example, if we say what is the gender of a person, it could be male, or could be a man, or could be like some other paraphrase. This is provided by the data set. Yeah. There could be some questions that have answers.
Well, but for some question, naturally there could be multiple answers.
Yeah.
How do they handle this?
This data sets, for those that have, for example, two entities, the answer is one person and the other person, because this data set is created by by looking at the Wikipedia, so that there could be a sentence, for example, Yizhou and Wei, for example, then this sentence is Yizhou and Wei, although there are two entities, but there is a single sentence that contains these three words, so that this is the answer. If they change the order, then it is not correct. Did I?
Well, it could like for example, the question could be that who was the like former president of the United States, and then in the document you could have Barack Obama or Bill Clinton or something. They're all correct, right?
Yeah. So
list like equally, or tell me one former president, right? Something like that. They're equally qualified, right?
Yeah.
As the answer. In that case, do they have some special treatment?
This data set don't have such questions, so that they are not that open domain. So all of the questions, their answers can be found in the Wikipedia passage. There could be a specific passage. For example, if there is a passage called Obama and Clinton appeared there, then this could be the answer. Did I explain it clearly?
Yeah. Okay.
This is
I mean, they both could be like, there could be in one passage there, like first they talk about Obama, right? And then they talk about Clinton, then they talk about maybe George Bush, or right. So in that case, how do they do that?
Yeah, I agree that this is a very like a significant problem for the open domain QA. So ideal case is like we have multiple entities and it is a set, so that we should extract multiple this kind of entities, and no matter what is their order, they are correct. We should extract a set. But in this, the limitation of natural questions is that all the answers are actually just like a span of.
So if like see in the same document, right? They have like 3 sentences talk about 3 different presidents, right? And in a similar way, they talk about that. And then once they train this model on that, would that confuse the model? Like if the question is like, who was the president, right? So would that, because you have three equally good answer, right? So I would be happy like if they tell me any one of those or any combination of those, but just because there are three of them look equally good, would that confuse the model so that in the end, neither get high score?
So at least for natural questions, their question will be very specific. For example, who is the 10th president, or who is the president that is elected at 2014, something like that. So all of the most of the question only will have a single answers. Even if they will have multiple answers, for example, there is a set, there could be two entities. They will appear in the context that there is a sentence called A and B. So yeah, they will be occurred like jointly. For those questions, maybe there's some confusion because, for example, there's a sentence called A and B, but if you retrieve A from the other places and you treat that as a negative samples, then that could be a false case in the fine-tuning stage because in the negative samples you will retrieve a very good candidate, but that is not correct. But the good thing about this contractive loss is that even if you have some negative samples in the like a denominator, it will not influence too much because we will have a log term, because we have a softmax in the denominator, so that even in the original formula we will have true samples in the denominator, so it doesn't influence the result too much. If you replace this loss as like a binary classification loss, then it will be a really big issue. Yeah.
Okay.
Yeah, this is a very good advantage of multi-class classification loss, which is very successful in the contractive learning recently, because there could be many like a false, how is it called? False positive in the denominator. Yeah. Okay. So after they do this query side fine tuning, they can get the answer in the inference. And they also add many other tricks. For example, they add a question generation module that utilizing a T5 to given the passage and the corresponding entity to predict to generate corresponding questions to enlarge their training sets. And they also add a distillation, which they since I previously said that they somehow train it in as a framework that they will have different encoder for the question and another encoder for the phrase, and no interaction between the phrase and the question. Although it is very fast, but that prediction accuracy is not good enough. So they add a distillation module that they first train the model that concat the question and the passage to extract. So it is very similar to the final reader model, and they use the predicted probability of the reader model as the teacher model to distill the knowledge to their the trained model. It also enhances the performance a little bit. So I think you are not very interested in this kind of tricks, but only by combining all this kind of like ad hoc tricks, they finally get similar results to the computer, like the retriever reader module.
So what would be their performance without those tricks?
Yeah.
How much does this trick help? That's my question.
The biggest improvement is this one. So the hard negative sample one, from let me can you see the paper? Yeah, because the time limitation, I didn't put all the results in the slides, but we can see that. Yeah, this is like an ablation study. So for example, adding the distillation can enhance about 2%. Adding the question generation can enhance about 3%. Yeah, these are the two metrics. And the other very important one is whether do the query side fine tuning. And this one influences quite a lot. If you didn't do it, the only result is about 29. And if you do the fine tuning, you can get about 41. So this called query side fine tuning is the only inference is the quality of the negative sample. In the previous one, without this kind of like the fine tuning, the negative sample are all the other word within the passage. But as I said, most of the other words are not that informative. They are not very strong candidate. By adding this, it enhances the performance quite a lot. So this is also observed in the DPR paper. In the DPR paper, if they added a hard and negative sample, the performance can reach about 40 to 42. But if they didn't add that and just randomly pick up the samples, the performance is quite low.
I see.
Yeah. So for this kind of both this could be treated as a supervised contractive learning. For both the supervised contractive learning and the unsupervised self-supervised contractive learning, how to select the negative sample are a very important issue in reality. Yeah. Okay, I think this is all about this paper. I think it's very, very novel as that it jump out of the previous framework that many people have tried to base on and improve their and improve their accuracy. But at current stage, both the performance side and the storage side has increased. It's not tolerable because currently the storage is still very large, and also as John suggested, there could be some phrases, for example, Obama appear multiple times, and they just treat them differently. This could also be one potential issue for both storage and accuracy. So I talked to the author of this paper, and they because it is actually rejected by the NACO, and their later plan is try to merge some of the phrases in the storage. To do, for example, like a cluster or the other things to eliminate some of storage, and tries to remove some of the this kind of implementation tricks, so that the model can be more unified. But still, I think that this is a very interesting direction that maybe later on researchers can follow up and enhance the existing QA models. Because real QA, if we want to deploy in the search engine or in other places, the throughput is very important. DPR already outperforms the previous ones that concat the question and the context. For those, the number of seconds per question could be hundreds slower than the DPR, and this one is even faster. So I think this is a very interesting direction, at least in industry level. Okay, these are all the papers about open domain QA. Later on, I will quickly show about several papers that are not in the space of open domain QA, but more in like the common sense QA or the other datasets. For those of the datasets, one like the phenomenon is that we will also have a knowledge graph given, so that for example, like a common sense QA, most likely we will have the word net or like a concept net or the other like the knowledge graph as a guidance to answer some questions. And all the three papers I will later on presented are follow the paradigm that they will firstly parse a subgraph that from a whole graph and tries to reason over the subgraph. So the first paper is conducted by Euro and Percy Liang's group. So Ren Hongyu, we are familiar with. He is the author of the KPQA, many of the knowledge-based query embedding, like the beta embedding and so on. And this paper tries to actually, it is not in the flavor of those paper, but tries to extract a subgraph and utilizing the BERT on that to extract the answer. Yeah. So the question scenario is that we will provide the candidate answer. So that's given the question and several candidate answer, they will first construct a subgraph and adopt a GN on that to get the answer. So the idea is actually not very novel, and there's already several papers ahead doing similar things. I just present this paper because this is the newest the newest one, because it is published in incoming NACO. And the first step is retrieve a subgraph, and they add a second step, which is to compute the relevance of each KG based on the question and context within this reasoning graph. This is like the most novel things they do. And the last is they perform the reasoning on the graph. And also they do a lot of post-point analysis of this framework, which is somehow different from the previous works. So firstly, I will introduce the overall framework. Yeah, so the retrieval subgraph part, they directly utilizing the procedure published 1 year ago by Renxiang's group. So they just utilizing all the entities do first doing the entity matching, extract all the entities within the question, and retreat all the answers entity as the seed node, and expand a K-hop subgraph. So this is like a very naive way and a very coarse level way to extract a subgraph. And they also observe that after they extract such subgraph, many of the nodes are not very relevant to this question, because this kind of K-hop expansion are not necessary to expand the neighborhood. They are relevant to this question. So they add a so-called relevance step by simply calculate the tax similarity of each entity with the question to calculate a relevance score. And after that, they conducted a GN on top of a subgraph to get the final answer. The relevance score, although it is a digit, but they embed this digit and as a D-dimensional embedding by a single MLP, and concat that into the node embedding, and put that into a relational attentional GN. So actually, this model is very similar to my HTT paper, and they didn't call it a name, but the basic phenomenon is that for different relation, they will have a different projection and calculate attention, aggregate that. And at the node level, they have the score embedding to differentiate how each node is important to the whole like the reasoning procedure. The relation is defined by whether each node is attached to the question or like the answer, or like expanded neighborhoods. Okay, so the model part, actually, I don't think it is very novel, and so I just quickly go over that.
So in the example, they show some like negative question, negative relation, but how the GN can handle that?
So they only calculate the irrelevant score. So for each node, they will calculate a relevant score, and as I said, they will embed that into a D-dimensional embedding, and add that into the node embedding. And by propagation, for those irrelevant to the node, probably they will have a lower attention value attached to them.
Yeah, I think I was talking about the first motivating example. If you go to slide 26.
Yeah.
26 can go with
26.
Yeah, you see, if it is not used for hell, it just wonder how that negation can be handled.
Oh, you mean this one? Actually, they didn't explicitly model the negation. This negation, from my understanding, is that they encode the question as a context node, so that this context node will somehow encode the information of the negation. And if they replace this negation, for example, delete it, then the context node their embedding will be different. And through the propagation, they can, based on the context node, to determine the whole attention score between each two nodes.
I see. So with the assumption that this knot will be
encoded in the, yeah.
Which
so
I think is very hard.
Yeah, but actually they show some of the example later. Yeah, I will show the evaluation later.
Okay.
So I think the reason they emphasize this negation is because like Ren Hongyu is very addicted in the in the how to handle the negation. So he thinks that this is about like a very challenging problem. So they add a whole section about how to handle such a structure reasoning. I will show you later. So on the leaderboard, actually, they are not the state of art currently. They obviously beat the previous baseline. Let me show. Actually, that baseline is not appearing in the leaderboard they show. Uh, yeah, but they are based on Renxiang's code, and from their code, they get about 1 to 2% of the enhancements. But overall, when they compare with the other, like based on the test leaderboard, they are not the state of art. But they claim that because of their model is have much lower, a smaller parameter. Yeah. Um, so later on, I will show some visualization, and they add a specific section about structural reasoning, which I think is somehow interesting. So first is about the visualization, since they have the attention value, so that they can obviously get the like the subgraph, like that, like a spanning tree by looking at how the question like attend to the other entities and finally get the answer. So this is like what they get by each step. They just pick up the top k attended nodes. For example, where would you find a basement that can be accessed by with an elevator? So that the first hop nodes are that attend to the question are the elevator and basement, and based on that, they will have building, house, and cargo, and finally office building and church. Among this office building is the final answer, which also have the highest attention value. Yeah, this one is similar. Crab lives in what sort of environment? So that the first hop are crab and salt water, and after that they will and after that the crab is connected to sea, and sea is also connected to salt water. So finally they will see that salt water is the final answer. Yeah, this is not very surprising, because I think most attention-based model can learn to solve subgraph. This one I think is a interesting data experiment they do. So they tries to explicitly focus on the negation and problem, so that they found all those questions with a not or a no, and they added two like controlled experiment. One is to flip the negation, the other is to change the entity. For example, the question if it is not used for hair around the brush is an example of what. So for this question, the answer should be art supply, and their model can predict art supply is the answer. And if they remove that not word, and firstly they can predict that the hairbrush is correct. And also, if you look at the attention map, like uh, yeah, I think the major difference is that in the previous example, if they said if not used for hair, and around brush is an example of what, because it is actually two separate constraints. First is that it's not used for hair, and the other is that around brush is an example of this. So that in this case, they will have a highly attend score from the round brush to a painting. But in this example, since they remove that not, so that based on the first constraint, they can already get the answer, so that they don't need the attention from the round brush to the painting. Yeah, and if they like to change the word from the hair to the air, to the art, to the arts, uh, yeah, to the art, and uh, they can also observe that uh, sorry, I don't fully understand how their attention map represents. Yeah, it is for this example, they can correctly identify that, but not quite sure why.
Is a question encoder come from BERT?
Yeah. So okay, I understand what this entity tries to say it about, because as I said, there are two like constraints. One is not used for hair. The other is round brush is example of what. So if they change the word hair to the art, the original answer art supplies should not be correct, because currently we have a constraint that it is not used for art. So that it should have a attention, it should have an edge between the art and the art supply, which have a lower score here because of the not used for art here. So that based on this change, they can predict that it is a hairbrush. So although the round brush could be either the hairbrush or art supply, but based on different constraint, they can go to different like the prediction results. Yeah, the initial like question encode embedding is from like BERT-based model. Yeah, they didn't give large scale like the experiments. They took only somehow like cherry pick some example to show that since they can encode the information from the question to the question hypernode, and this question hypernode can influence the attention result of the other nodes, and so that their model can model this, their framework can model this negation.
Yeah, based on this, then it seems to me like the BERT model actually also very sensitive to the negation. Is that the common sense?
Yeah, so if we have the like tune the model, for example, in the supervised data set, we have multiple tasks that is very sensitive to the nodes, then BERT can like somehow like they identify those patterns.
Okay,
Yeah,
depending on the like task. Okay.
depending on the task, yeah.
Okay.
If you didn't have too much of the task that relevant to the node, then things like the BERT is trained based on the context prediction. Whether there exists a node or not, whether there exists or not, will not like influence the other context, so that maybe the embedding will not change too much. But obviously, they will have the ability to identify this pattern during the fine tuning.
Mm-hmm.
Okay, so this is for this paper, and so this paper conducted common sense QA with the answer, and also there's like another NACO paper conducted by Lin Yuchen during his intern in Google, and they tries to propose a novel task that doing the common sense QA without the answer. So this could be a hard task because many common sense QA's questions are are very hard and like highly depend on the some common sense property of the entity. And if you don't provide the answer, then directly doing the BERT-based model might not capture those word knowledge, so that they are not very capable to do that. So that they tries to propose this task and handle it by their new framework. The major challenge is that firstly they require latent multi-hop structure. Uh, since they don't currently have the answer, so that if they want to infer a subgraph, they cannot utilize the answer as a seed node. So that the only thing that they can refer is the question, and jump from the question to the graph. Is a very challenging thing because unlike the Hopper QA, which is a multi-hop QA question dataset that provides the intermediate reasoning path, their setting don't have this kind of latent multi-hop structures, so they need to learn it end to end. And the other is that obviously the final answer space is large, so that they need the efficient way to do that. Yeah, obviously they cannot do concat the question and each of the answer to do to get the results. So the model part is exactly the same as the differentiable reasoning paper in Williams' group about 1 year ago in ICLR conference, which I have already introduced in the previous quarter. So that I will quickly go over that. The basic idea is that they will build a binary, a bipartite graph of each entity with the document that contain this entity. For example, suppose there's a document called "Tree removes carbon dioxide from the atmosphere through photosynthesis," so that this document, this like the sentence contains the entity trees, carbon dioxide, atmosphere, and the photosynthesis, so that this tags will be connected to all these corresponding entities. And their overall the objective is that given the questions, each step, they will do iterative step. Firstly, to retrieve the corresponding entity from the question, and then based on from this entity to go to the fact, which are the sentence that is most similar to the current entity that occurred in the question. And after that, given each current facts, which are the multiple sentences, and the question, they will jump to the other entities, go back to the entity space, and then from the entity space go to the fact, so that by iterative do things like that, they can finally get the final answers as the entity. The basic framework is like this. The dense index of fact vectors are the embedding of each sentence. This sparse matrix of fact links are the all the sentence to the entities, and then based on the current entity embedding, not entity embedding, the sentence like the activation embedding, which means that which sentence they currently retrieved. In their cases, this kind of fact embedding is actually like the not so sparse. It's like a dense embedding, which means that they can have 0.7 probability to retrieve sentence 2 and 0.1 probability to retrieve sentence 3. And then based on this probability embedding, they can retrieve the entity embedding based on the sentence to entity matching, like the linkage, like the adjacency matrix. And after that, they will also have a mask based on the like embedding similarity of the sentence to the question to mask out each of the entity and finally get a next hop. Yeah, I didn't introduce this too much because firstly, this is like a framework in 2 years ago, like of the DR fact, and also this like a very complicated framework didn't seem perform better than the simple DPR paper. So I didn't spend too much time to explain it. But since he is interning in the Williams group, so that he directly utilizing Cohen's framework to deal with that. Okay, here is the final evaluation of and obviously by expanding their subgraph based on this kind of bipartite graph, they can retrieve better results than the single BERT-based model. And also they compare with DPR with the simple retrieval, and by adding this kind of the subgraph expansion, because this is a common sense QA data set, the knowledge graph is obviously useful, very important, so that they can get better results than the DPR. Overall, these two papers tries to expand a subgraph based on the questions to get the final reasoning. The main difference is that the first paper I introduced is firstly construct a subgraph based on the heuristic, and then calculate the importance of each node, and then doing the message passing based on GNN. The most important step, which is the first graph construction step, highly rely on the answer. The second paper, because they don't consider the answer, so that they cannot get an initial good subgraph, so that they expand on like the entity expansion mechanism. And to do that, they use like a framework published 1 years ago to step by step expand their entity sets. Okay, I think here are all the QA papers I want to introduce so far. Do you have any question about this too? Okay, if there's no question, since there's like 20 minutes left, I also like prepare several slides about the recent advance of the image transformer. Yeah. The reason I want to like emphasize this one is just because like about several months ago, MSI's group like proposed a swing transformer and adopt really like a significant performance enhancement compared to the existing state of art like the ResNet. For example, from this segmentation, like the image, we can see that their transformer result and enhance about like 6% of the like the MMOP compared with the previous ResNet based model. So I think maybe it's important for our group to at least know about like this recent advance. So the general idea is that of adopting the transformer into the image domain is that they tries to first they segment each image into multiple patch. This is like firstly introduced in the ICLEAR paper 1 year ago by the Google Brains group. They're following this idea, all the other things are very straightforward. Based on the single image, they first segment it into multiple patch. And since each patch will have a corresponding position, so they can easily add a position embedding to them. And they put all these patch into a like the vanilla transformer model to learn the mutual attention. The major difference of this kind of model with the CNN-based model is that CNN didn't have the global interaction between two like the like a disconnected patch. Most likely, the each CNN like a convolution layer only have a very small range of the receptive field, and only if adding many deep layers, they can somehow get the global information from the other side. But utilizing the transformer, we can easily get the global interaction between each patch with the others. Yeah, and this is like the overall like the modeling. For each of the patch, they will have an initial projection to encode them into the initial embedding, and they also add another special token similar to a BOS token in a bird to as the output of for classification, and add a position embedding to them. So although we think that in image probably the position of the pixel as the XY axis like 2D position should be more advanced than 1D, but their evaluation shows that just adding 1D is enough. And also the initial embedding this E can also be replaced by a CNN model, yeah, as the initial feature extraction. Yeah, at that time, at 1 year ago, their VIT visual transformer model didn't perform much better than the ResNet-based model. As you can see, there's still some performance gap from the visual transformer to the ResNet. But the advantage is that since transformer model is much better for like the for parallelization, so again the throughput of the visual transformer is better than the original like the ResNet paper. So that as you can see, also we can see that adding the position encoding can benefit the model to learn some of the basic visual patterns. For example, this is like the input layer. We only capture some of the low-level patterns of the image, and this is like embedding visualization. You can see that for each of the embeddings, they will have pose higher attention on those patches that are near to it, that which is reasonable. Finally, this is like a global attention matrix visualized on each image. As you can see, for most of the, not most of, actually for all of the cases, they can identify the most important object for image classification. But still, this paper have some limitation. First is that if we have a very large image, for example, not for image classification, but for semantic segmentation, where within an image we have thousands of entities, and we still need a very high resolution of the image, then the pixel, then the number of patches will go very large, and in that way, both the computation and the like the like and the model generalization will be influenced, because the model have too large of the parameters. So about months later, this MSRS group proposes swing transformer by adopting the hierarchical patches, and they use a trick of shifted windows combined with local like a patch attention to reduce the complexity of the model and achieve the the best results actually on most of the most important benchmarks in computer vision. So this is like an overall difference of the student transformer and visual transformer. So basically, it's like they will have a hierarchical of the patches. In the lower level, the patch size will be very small. For example, initially like the patches is 4x4, and later on it could be 8x8 and 16x16. And in the lower level, they don't utilizing global attention of each patch with the others. Instead, they only consider a smaller region, which is like anchored to the upper level of the patches. For example, this patch is corresponding to this 16 smaller patches, and this 16 smaller patches only connected with all each other in their base mode, in like the original design. In this way, sense of the local attention like interaction, the overall complexity for calculating attention can be largely like reduced, and in that way they can get more fine-grained patches to those high resolution images. But if they if in their original design each patches only consider their local neighborhoods, then there is still some of the degeneration of the performance, because we don't add the global interaction between each window to the others, so that they add a very I don't know how to call it, very complicated strategy called swing window. The basic idea is that for each of the patches, they will shift the window to the middle. For example, this is the original one, and at each stage they will shift it from x-axis and y-axis by two times two, like for example to be at like this. By doing so, they put these two transformer blocks into adjacent layers. In this way, even if a single patch is in the original block only connects to their local neighborhoods, but in the next like the patch design, since they shift the window by like a small patch, that local patch can interact with the other side of the patches. For example, this patch in the original block can only interact with this one, but not to this one. But later on, if they shifted the window, they can interact with that one. So by shifting this window for each iterations, the image can, for each of the image, their receptive field can be doubled for four times. Yeah, and they added such like aberration study to show how this shifted window benefits, and for those like the task which require finer granularity, like the semantic segmentation, this shifted window size can enhance about 3% of the enhancement. Yeah, so the overall idea of the transformer, a visual transformer, is not very new because we all know that transformer works in attacks. But only recently, after the bird, people realize that how significant it is to handle like the both attacks and image. This is why recently there's lots of groups tries to merge the transformer into the vision, and the the basic challenges for vision is how to define such patch, and the position most likely is just the position of the patches. And IRG recently also tries to think about how transformer can work for graph, but for that one, also we have the patches issue and also the position issue, and I think that kind of research overall like is in the line of these trends that transformer can be model anything. Okay, I think that's all for my today's presentation. Any questions?
Yeah, I'm good. I think I don't know. I just feel like the last two papers probably can also give some inspirations in design graph neural networks. And some of the ideas I think we probably have already utilized, right? For example, the hierarchical structure of the graph.
Yeah, hierarchical graph is somehow similar to graph pooling. Yeah.
Right. And also when we try to kind of do the graph neural network, instead of just look at the local neighbors, we also try to see whether we can somehow connect to the nodes or other regions that are relatively far away from us, right? So we can do this by, for example, using clustering or like use subgraph level kind of learning.
Yeah, I think the major difficulty of applying like this kind of visual transformer to the graph is firstly the position of each node within the global graph is hard to define. So that unlike the position in the pixel, you can simply regard it as a first pixel or second pixel. But for the graph, each node doesn't have a static position. Also, for this kind of a patch grouping is or in the graph is like subgraph grouping is not a very trivial things. We cannot simply get a 4x4 patches, but we need some of the like the advanced design to get the subgraph pooling. Otherwise, the performance will be degenerated quite a lot. Currently, most of the graph classification benchmark, their best model are not with the pooling method. So I still think there's a lot of space to enhance.
Right. I think this, if we just look at the left plot, I feel it's very related to this hierarchical clustering or hierarchical community detection in graph. But
Yeah.
somehow I think in vision, they have this very complicated task. But in graph, right, so if we look at our current graph classification task, I mean, the benchmark data sets, probably they are not powerful enough in differentiating all kinds of algorithms.
Yeah, so at least we currently have a chemical classification task. For example, in the OGB LSC, which is a very large scale chemical property identification task. And their benchmark shows that the performance gap between two models are already significant. So this is what we try to enhance currently. But obviously, for graph, a very challenging thing is that we currently don't have a killing app compared with machine translation or image segmentation or others that have real usage in real world. But currently for graph, most of the tasks are not very useful in the industry level, and also the scale are not too large, and the difficulty is not too high. Yeah. So which task should we explore later? I think is a very important things we need to discuss. Yeah. Also, the reason why visual transformer recently grows a lot of attention is that people tries to unify the visual and the text. I believe most of you are notable of the OpenAI's DALL-E's work that tries to embed both the image and text and do the generative model, so that given that a short text description, they can generate high fidelity image and vice versa. And their model is based on the visual transformer, so that they can unify both domain together. I think this should be the trend for the later on machine learning model design, so that people don't have to design very complicated intermediate model.
Yes, that's kind of bridge the gap of different modality of data. So essentially, we
Yeah.
talk to each other. It's just a different different format of the sharing information among people, but actually they carry the same thing, right?
Yeah. This is why I think maybe this is a trend, and yeah.
Yeah, sounds good.
Okay.
Okay.
Thank you so much. I will stop here
Okay.
and see you next week.
Yeah,
Bye.
sure. Thank you. Bye.